We are into Chapter 9. So let's get into gas power cycles. One is, this is the longest chapter in the textbook, but I think a lot of students find it very informative, helpful, exciting. It starts off with internal combustion engines, things that make your cars go, things that make your lawnmowers go, things that make your weed eaters go, things that make your, just internal combustion engines. They're all over. And we'll cover again the Otto and the diesel cycle. These were covered in Thermo 1, but we review them again because they're so important. Then we'll do gas turbines, both for the stationary power plants. Typically, this model is a Brayton cycle. Then you can have enhancements to the Brayton cycle, regeneration. Is that the same word we saw for the vapor power cycle? Did they talk about regeneration? Yes, they did. How about reheat? Was that the same concept also for vapor? Did they have reheat? They sure did. Intercooling? No, not for vapor power, but definitely for gas power, the Brayton cycle. And so there's an enhancement there. Now, you'll talk about superchargers, turbochargers for, let's say, the Otto and the diesel engines, true? And in there, they'll have an intercooler, true? Same concept here. Good for performance for air power cycle for the Brayton. It's good for performance for the Otto or diesel cycle, intercoolers. But I don't think we emphasize them here, but we do here for the Brayton cycle. Now you can also have gas turbine engines for propulsion. This is what makes a large number of our surface vessels in the Navy work. Okay, is a gas turbine. It's like, yeah, they used to have a lot of piston cylinder diesels, but there's a lot of gas turbines. Helicopters, gas turbines. Aircraft, not all, but there's a vast majority of what you fly in an aircraft, in military aircraft, are gas turbines. So there are a lot of gas turbines made to move us and other things around quickly, and they're very powerful. And then we deal a little bit introduction to compressible flow. That's Chapter 9. They could have busted it in 2 or 3 chapters, but they put it all into one big chapter, so it's a little long. Well, this terminology of internal combustion engine, if somebody said change it up a little bit, you'd say, oh, how about external combustion engine? And that's what they used to have. And here's an illustration found out there on the internet of where they used to have a steam engine, and they would burn the coal somewhere external to where the steam expands. So where the steam expands and you're getting work out in here, that's called external. External combustion to where the piston's being pushed back. Internal means that that's where the combustion's occurring and it's pushing against, right intimate with the combustion is you're pushing back the face of the piston or the top of the piston. So that's hopefully trying to explain that term. I understand combustion engine, you're burning some fuel, but why internal versus external? There you go. Reciprocating, these are one of these great things. I still remember when I was very young and I finally figured out, wow, that's how an engine works. So the piston's sliding up and down, it's reciprocating in a cylinder. I don't know if you remember any joy like that. It's like, wow, this is so neat, And you look back at it and say, well, okay. But, I still remember being very excited figuring this out. So the cylinder is stationary and the piston slides up and down. It's reciprocating, going back and forth. And you get out of it the rotary motion, rotational motion of the crankshaft. And there it is, the beauty of the crankshaft. That offset that makes it go around. Right? So, but we're going to study this reciprocating motion, the piston going up and down, and then we'll leave it to your other classes, mechanisms and other things about translation and rotational, from translational motion to rotational motion. But one of the things that you'll look at is we'll talk about looking at this way on the crankshaft. And we start with a connecting rod, and the connecting rod rotates 1/2 a rotation. When it rotates 1/2 a rotation, it brings the piston from the top down to the bottom. See that? The piston now goes from top to bottom. So we'll talk about, the piston's at top dead center. And now, okay, half a crank, half a rotation. It's now at bottom dead center. See that? So maybe I'll draw it again. This length is the same right here. So I'm not going to try and change that length, but I'm going to try and put it over here. And now the piston's here. So the piston went from top dead center to bottom dead center with a rotation of half a rotation of the crank. If you do another half, the piston goes back from bottom to top. So one complete rotation gives you how many slides or strokes of the piston in the cylinder. One stroke down and then one stroke up. So you got 2 strokes for one rotation. Then if you do another rotation, you get 2 more strokes. So you basically get 4 strokes. And what we'll find is we need 4 strokes to complete a cycle. So it's a 4-stroke engine or a 4-stroke cycle. 4-stroke cycle. You'll see that out there. Now, somebody says, I buy a weed eater, I'm using my weed eater, I have my gasoline, they tell me to add oil to it. And then I ask myself, hey, I know my car, I need to change the oil every now and then, pull the plug in the bottom of the oil pan and change the oil, change the air filter. I wonder where the oil pan is for my weed eater. Doesn't exist. Where's my oil filter for the weed eater? Doesn't exist. True? So there's something very different about your weed eater engine and your car engine. How many people own or ever been in a boat where you have an outboard motor or something and 10, 15, 20 horsepower? That engine, you mix a little oil with the gasoline, true, and then it runs. And then you ask yourself, hey, where is the oil pan for my outboard motor, my Yamaha, my, what is the big manufacturer of these outboard motors? Johnson, yeah, Johnson, some other ones, Where's the oil pan? I want to change my oil. It doesn't exist. Where's my oil filter? It doesn't exist. It's a 2-stroke cycle engine. Weed eaters, outboard motors on your boats and that are all 2-stroke. And then your car, your diesel, they're all 4-stroke. And right there is your translation, okay? You've got to go a stroke down, a stroke up, a stroke down, and a stroke up to complete a whole cycle, to redo it again. So you have to have 2 revs of the crank for one complete cycle on a 4-stroke cycle. You only need 1 rev for a 2-stroke cycle. But I don't really spend much time talking about it. It's another one of those marvels. It's like, how do you get it to work with 2 strokes? What is a 2-stroke cycle? And it's, if you know already, that's great. But you could take your weed eater apart before you throw it away. Strongly encourage. You only make it for so many hours. And you have big item trash pickup in your neighborhood. You see somebody else, your neighbor's throwing it away. Go over there, take it off his pile. Take it apart, figure it out, and before they come pick it up, throw it back on his pile. Your education's free, except for maybe a little embarrassment that your neighbor says, what are you taking my trash off my pile for? But really, take things apart. They're really helpful. Now, here's a typical engine, and they have a lot of names of parts, and you can be very confused. But as an aspiring mechanical engineer looking to graduate within a year, year and a half, you really don't want to say, what's that? Really, you should. I mean, a mechanical, this is our domain, true? Engines. So you should be able to, so take that engine apart off your neighbor's trash pile or your engine before you throw it away, and just learn how to call all the parts. And so I typically cover up the part names, and then I say, what is that? Okay, looks like what is that? Camshaft. And you have 2 of them. Dual overhead cam engine. Hey, we've seen that. A lot of times they only have 1 cam. Here they have 2. What's this thing? Spark plug. And here's a way to get stuff in, and here's a way to get stuff out. That must be the intake and the valve controlling the intake, and this must be a valve controlling the exhaust. That's right. And those look like springs, valve springs. and then the cam rotates on a lobe, and it pushes down. This is great. I still remember it. Wow, that's how it works. This is incredible. So as it's rotating, it's smooth here, and then it hits a lobe, and it pushes down and makes that valve open, and then it goes back. That spring makes it go quickly to close when the lobe passes in rotation. In here is the combustion chamber, and they draw a little line separating here from here, so everything above is like the head. You say, oh, got a cracked head or some problem with the head. Oh, just a head leak. Yeah, right. Never buy an engine that just has, just a little head leak. Yeah, it's a big job, no matter what. And then below is the block. And in the block, they're even showing you maybe this is some coolant passages for Gatorade-looking antifreeze. True, often it's green, sometimes it's yellow, but that's why I think they colored it that. And if you have a head gasket leak, oh boy, big job. Yeah. This is the piston, and it slides back and forth, and it's through this connecting rod. So that's connecting rod. Down here is the crankshaft with a little bit of an offset between the center of the connecting rod and the center of the crankshaft. That offset determines how much stroke you get. This distance right here, you just say, hey, I think that's the distance that you're going to go. Two times the offset is the stroke. 2 times the offset, crank offset. Oil pan down here, whatever. Here are the names, but you can go and look up things on the internet. And I strongly encourage you to try to test yourself and quiz yourself as you're trying to learn material by covering things up and then repeating.
We're not going to go over any exotic engines that we like to go into.
No. Sure do not. Yep. Also, you can find great things out there on the internet about understanding the 4 strokes. So I like to put, and rotate, go intake, and then you have compression, then a power stroke, and then exhaust stroke. All of these you've been exposed to at Thermo 1, but take a look at them. Here is a little illustration that's out on the internet. And what I like about it is that I can open it up and I can run it. So if we hit start, or hit reset, okay? What they're doing is they have a piston, and it's going to be starting to move. And as it moves, you can see the location on a pressure volume diagram, a little trace, that little dot, you can watch it. Let's hit start. And if it's supposed to, and so it's starting to come down. You could see it rotating with the crank, so you get that mechanism. Here's the volume is increasing, and then it hits the bottom dead center. Now the volume's decreasing, the pressure's going up, so it's in the compression stroke. And then something happens, ZZ. Oop, look at that, it turns red, and the pressure skyrockets at constant volume. And now it's going down and expanding in the power stroke. The pressure's still high, and then you come down here and it rapidly drops. That's why you have mufflers. And there's a big blowdown. And then you pushing it out. This valve now kicked open. The exhaust valve is open. You're pushing it out. And then your valve closes. This intake valve opens. You're starting now again that intake stroke. Notice the pressure is low on the intake. It's a vacuum. It's a slight vacuum in the engine, right? If you have a vacuum leak, okay, that's why. Air is getting where it shouldn't get into your engine. So you can trace this around. You see this is modeling a 4-stroke cycle, like an Otto Cycle gasoline engine. And you could just watch this a few times and you'll see, okay, I got the picture. A lot of exhaust goes down in the blowdown. Right now it'll be a big rush when that cracks open. Boom, right? Especially for engines under a load. You have a higher delta P right there. It's Mach 1. It's loud. That's why you have mufflers. And then it's above atmospheric pressure as it pushes it out through the exhaust manifold, catalytic converter, muffler, tailpipe, and then finally out. Yes?
So when you start your car, are you already in the compression stroke?
You're somewhere, anywhere. And so it'll just go until it hits a spark, and then you kicked it. But Typically, if you're running, let's say, 2,000 revolutions per minute down the road, that's not very fast either. A lot of engines are going fast. You could find out it goes through a cycle pretty quick. It really goes through a cycle. And then you can do this. You're driving to Houston. Oh, let's see. My tax says I'm at 3,000 RPM. I'm going to be driving here for an hour and a half. I wonder how many times the piston goes up and down in my engine. And you just do some mental math, and you'll be amazed. I wonder how many times that spark plug is going to fire. Oh, I have 4 of them. Oh, I have 8 of them. You know, how many times does it fire between here and Houston driving for an hour or so? You'd be amazed. I put 100,000 miles on my vehicle. Should I change that spark plug? I wonder how many times it's fired. Change that oil? You got to change your engine now. Maybe the synthetics are getting that good. I know you can go a long time now with synthetic oil, but are they rated 25? Easy, yeah. All right. Now we jump over to air standard analysis. We want to analyze and make a very simple calculations. This is a complex system. We make some abstractions or simplifying assumptions, and then we can analyze it. So what we do is we say, oh, if we're going to do an air standard analysis, we're going to assume there's a fixed amount of air and it's completely trapped in the piston cylinder. There's no intake and exhaust valve to let it in and out. It always stays there. It never is converted to the products of combustion are CO2 and water when you burn a hydrocarbon. We're just going to say it's always air. We can now model it easier. It's always an ideal gas, which is a good assumption, even for the exhaust products. So PV is equal to RT, U is a function of temperature only, and H is a function of temperature only. Those are the 3 things you need to remember about an ideal gas. Also, combustion process is replaced by a heat transfer only from an external heat source when the piston is, oh, I forgot that acronym, TDC, TDC. Top dead center, top dead center. And there's no intake or exhaust process. And the exhaust and intake really is replaced by a heat transfer to an external heat source when the piston's at BDC, bottom dead center, when it's at its maximum volume. And all processes are internally reversible. So let's ignore friction. Why? Why do we make this simplifying? So we can do something, so we can make some calcs. Otherwise, the real world is too hard for us to do anything on pen and paper, right? So now we can make some calcs. In addition, you'll see this. Oh, we want to do a cold air standard analysis. Everything that was stated above, because it's an air standard analysis. But in addition, cold meaning we're going to assume constant specific heats, and we're going to evaluate those specific heats at atmospheric temperature, 25 C, 300 K, somewhere around there. Why do we even make that cold air analysis? Because it makes it not only doable, but it makes it where you can package up and have some really important results, like, you know, the overall thermal efficiency of let's say an Otto cycle can be a function, an analytic function of the compression ratio. That's incredible as a result. Okay? Let's go to the Otto cycle. This is modeling the gasoline engine. Okay? You have a diesel cycle. I wonder what fuel engine that one modeled. The diesel. Okay, right? So if you have a gasoline engine, this is the 4-stroke Otto cycle. All right, so you have processes. You have from state 1 to state 2, that's a process. And then from state 2 to 3, 3 to 4, 4 to 1. On the PV diagram, we had a compression stroke, a combustion, then we had the exhaust and the intake, and then it went around, right? That's too complicated. So we replace it by a simple analysis that says, I'm going to start with the piston at the largest volume. Is that bottom dead center or top dead center when the piston's way out here? Bottom. Large volume. And then I compress. I go through a compression stroke. That's right. Now I'm at top dead center. Top dead center. Then we go through some heat addition at constant volume at top dead center. Then we go through an expansion to bottom dead center, and then we go through a heat rejection. So here's our Q in, Q in. And now let's go ahead and number these states. 1, 2, 3, 4. So the process between state 1 to 2, 2 to 3, 3 to 4, 4 to 1. So for our cycle, we have 4 processes. And this Q, 2 to 3, is our Q in. And I'm going to draw it like this. Q 4 to 1 is not really in. We're going to find that that's negative because it's rejecting heat. It rejects heat there, 4 to 1. All right. Now, so the first process is adiabatic compression. What is the, sometimes they'll put a little dash line like that, meaning adiabatic, meaning there's no heat transfer. True? And then you have constant volume heat addition. And then adiabatic expansion, power. And then constant volume heat transfer, and here it's rejected. It's rejected. The heat is rejected. We can write the first law for a process, for a closed system, closed system undergoing a process for each of these processes, 1 to 2. Is this a good representation? Do you understand this first law equation? Is it U2 minus U1? We neglected changes in kinetic and potential energy. True? Now, for the first process, it's adiabatic compression. Which of the terms in the first law is equal to 0? Which one? Q is equal to 0, is it not? All right, let's just take a look at the second first law statement. It goes from 2 to 3. For process 2 to 3, constant volume heat addition. It's okay. Which of the terms in this equation is 0? Work 2 to 3 is 0. Why is work 2 to 3 0? Because there's no volume change. The boundary work is integral P dV, no V change, boom, no work. And then it's adiabatic, and then same, there's no boundary work for 4 to 1, true? So, if you're interested in making some calculations, you continue to go back to the first law analysis and you start to make some calcs like, oh, I can calculate this work 1 to 2, I can calculate Q 2 to 3, etc. And then often your bottom line is what is the thermal efficiency? What is a thermal efficiency? Is it work net divided by Q 2 to 3? Thumbs up if you agree. Yeah, right. It's work net divided by Q 2 to 3. This was the only in. True? That's the only in. All right. Hey, I forgot to sketch the temperature entropy diagram for the Otto cycle. Well, I say that as I'm showing it's a positive in, and it's going to be a negative quantity because I know it's out. So, but when I write it like this, I wanted to be consistent with the application. So here, this 4 to 1 is negative. I expect a negative answer for that Q 4 to 1. And if it's positive, I made an error. Right. Okay. So, but what does the temperature entropy diagram look like? What about the process from 1 to 2? What's it look like? Well, it won't be a square, but how about 1 to 2? Like that? Is that 1 to 2? Why is it constant S, 1 to 2? All processes are reversible, so no entropy generation, and no Q, so I'm not bringing in or taking out any entropy with the heat transfer, and I'm not generating. So you could write the second law. I didn't really do it, did I? But you find S2 is equal to S1. What about 2 to 3? Temperature definitely went up, heat addition, and entropy went up, true? Along a line of what's constant? Volume, constant volume from 2 to 3, true? And then what do we have from 3 to 4? And then back again. And what's constant? V is equal to constant. So there's a temperature entropy diagram for the Otto cycle. Ready to solve a problem? Oh, before we solve a problem, I need to do a little more review. If you have constant specific heats for ideal gas, then if you want to know the change in internal energy or the change in enthalpy, it's just C sub V times delta T or C sub P times delta T. Do you remember that? Do you remember that? Right? Yeah. So there you go. So it makes it really simple when you have constant specific heats. If you want to evaluate changes in internal energy or change in enthalpy for ideal gas. How about change in entropy? Remember this equation, true, for constant specific heats. This is the most popular, C sub P natural log T2 over T1 minus R natural log P2 over P1, true? True? Yeah, but this is its cousin equation. You do a little algebra and you can derive or reestablish that equation, okay? You don't want to forget these. You don't want to forget them. Also, you can manipulate this further if you have a special process. That special process is called isentropic. Ooh, all these words. What does isentropic mean? Constant S, constant entropy, right? So if you have S2 is equal to S1, that means this is 0 for an isentropic process, true? And now I can rewrite this as C sub P natural log of T2 over T1 equal to R natural log P2 over P1, true? I can bring that C sub P over here, true? I can exponentiate both sides, T2 over T1. Well, actually, when I bring it over here, I get that, but then I can also put it natural log of P2 over P1 to the power R divided by C sub P. Now I exponentiate both sides, P2 over P1 to the power R over C sub P. True? But there's a relationship between these R's and C sub P's and C sub V's. We recall K, like this constant K, is equal to C sub P over C sub V. True or false? And do we recall that R is C sub P minus C sub V? There's a relationship between C sub P, C sub V, and R. And that's it. Do you recall? We could go back and reestablish it. But what you do is you have this R now over C sub P is equal to C sub P minus C sub V over C sub P, true? Which is equal to K minus 1 over K. Thumbs up if you agree. So now we can get, hey, that's equal to P2 over P1 to the K minus 1 over K. At this point, we do have equation sheets, and you can say, I know how to rederive that, but in the interest of time, I'll just use the equation, knowing how to rederive it if needed. But we did a quick sketch of rederiving it, okay? There's a couple assumptions. One is it's ideal gas, constant specific heats, and it's isentropic. How many people will use this for non-isentropic, in the vapor dome? I gotta have an equation. I better grab one. This looks like it'll work. Let me try it. Okay, you need to know when you can use it, when you can't. Similarly, you can relate the changes in temperature to changes in volume for an isentropic process, ideal gas, constant specific heats, as well as pressure volume. Often we write this like PV to the K is equal to a constant during that process from 1 to 2. Well, if it's equal to a constant, that's the same constant at the beginning of the process as well as at the end of the process. Hey, you get that result. There's different ways of showing these equations. Let's solve this problem. An Otto cycle, and we want to do a cold air standard analysis of it. It operates with 300 K and 95 kilopascal at the start of the compression. The compression ratio is given as 9.5, and the maximum temperature is 1100 Kelvin on the basis of a cold air standard analysis using this value for C sub V, this value for C sub P. Determine a bunch of stuff. Make a sketch. Probably a PV is good. something like this. So we want to stay with the textbook's numbering system, which is helpful, and I think it's very common. Start 1, and then go. So also, you really only have V when it's at bottom dead center. V1 is equal to V4. And you only have V at the top dead center. 2 is equal to V3. True? Only really 2 specific volumes. And the compression ratio, R, is the ratio. It's a number greater than 1. It's 9.5 for this problem. R is V sub 1 divided by V sub 2. Is that true? But is it also V sub 4 divided by V sub 3? It is also that. But this is the compression ratio, which for this problem is 9.5. Okay. What you do is you go ahead and say to yourself, I want to analyze the process from 1 to 2 and make a table to help organize all your information. You can do this one for the state 1, state 2, state 3, state 4. What is the pressure? What is the temperature? Let's see, they gave me the pressure of 95 kPa at state 1 and 300 Kelvin at state 1. What other piece of information did they give me? So what is that maximum temperature? It's at state 1, 2, 3, or 4, or somewhere in between. It's at 3. Is that true? Is it 1100 Kelvin? So I have 3 pieces of information already in the table. True? If you wanted to, you could put in volume here or something, but we really need U's. We're going to need U's. Okay? Or let's do this. Let's write down the first law. And so for the process 1 to 2, we had U2 minus U1 is equal to work 1 to 2. The Q 1 to 2 is 0, right? Okay. So how do I calculate this work 1 to 2? And how do I calculate this the temperature at the end of the compression stroke, which is T2? I'm looking for T2 and I'm looking for work. So I'm trying to solve for what I would do is try to get this table completely filled and then get every work and every Q that's non-zero. Okay? So if you go from 1 to 2, is it S is equal to S? S equal to a constant? S is equal to a constant. So can we write the equation that we just had derived? Can we say that T2 divided by T1 is equal to what? What is it? Okay, it's equal to V, what? 1 over V2 to the K. Help me now. Is it K minus 1? Take a look. We're using this equation right here. It's to the K minus 1. True? And so this is equal to the compression ratio, 9.5 for this problem, to the K minus 1. If you do K minus K for here, this problem, it's about 1.4. Those values, C sub P over C sub V, gives you K of 1.4. Okay? So if I make that calculation, I find T2 is equal to T1, 300 Kelvin, times 9.5 to the 0.4 power. And now we can write in what is that temperature. What is the temperature? Oh, it's around 738. I mean, we can put a 0.2 there, but okay, it's around that value. Okay? It's definitely not good to 5 digits. This is already a cold air standard assumption. It's not like you can hang your hat on it. All right, what about the pressure? A couple ways of doing it. You can go back and go P2 over P1 is equal to V1 over V2 to the K. Right? That's using this equation right here. True? And same discussion, you know that that's a compression ratio to the K power. And you calculate that the pressure is, for this problem, 2, 2, 2, 1. There's another way of doing it. Can you say, without using this, can you say that P1 V1 divided by T1 is equal to P2 V2 divided by T2? Can you say that? Yeah, you sure can. And so if you do that, you get the same value of P2. Okay? So, well, we already used entropy to get T2. And so that I'm saying you got T2. So using T2 from the entropy calc, this will work as well. They're all, that's right. That's right. Now, what about the pressure at 3? That pressure at 3. You have to use something like this to get the pressure at 3. So the pressure at 3, V3 divided by T3 is equal to P2 V2 divided by T2. The volumes are the same. True? And they gave us T3. You know, in these problems you see a pattern. They pretty well always tell you, oh, the maximum temperature in the Otto cycle is this. Okay? They can change it up a little bit, but often they tell you the maximum temperature. So otherwise, you don't have one equation with one unknown. You'd have to do a little more work. But there you go. So we get a pressure, of 3309. How do we go to get 4? Well, this is the way I think about it. You compressed from 1 to 2. You expand from 3 to 4. So it's like the compression ratio is now 1 over 9.5 going from 3 to 4 because it's not compressing, it's the inverse, it's expanding. So if you want, you can write like this. You can write something like, okay, T4 divided by T3 is equal to 1 over R to the K minus 1. Okay? Or you could think of it this way. What happens if I started at 4 and I compressed? Would I get T3? Sure. And so you could write T3 divided by T4 is equal to R to the K minus 1. Isn't that the same equation? Sure, but a slightly different thought process to get me there. You have to struggle through, make sure it makes sense to you, right? So you can calculate the pressure and the temperature for all of those states. Now, once I've done that, then I can come in here. Well, first of all, I did calculate the answer to part A, true? So the peak temperature, the temperature at the end of the compression stroke, that's T2 is around 2220 Kelvin. That's part A. What about the peak pressure? That would be P3 is 3310 kPa, something like that, right? Is that right?
Get your temperature and pressure. You said 2220, so you said 38.
I sure did. You sure did. Thank you. 738 Kelvin. Thank you. And now the pressure, I think I have right, 3310. Good. Now, what about the heat addition for the cycle? Well, this is where you have heat addition. So let's analyze process 2 to 3. Actually, I encourage you to analyze process 1 to 2, 2 to 3, 3 to 4, 4 to 1. Analyze them all. Get all the Q's and all the W's. All right? Then you can be a little more strategic at times. Say, I only need this Q. Let me get it. But the first time through, get all the Q's and all the W's. And this is U3 minus U2 is equal to Q1 to 2. So this equation I use to calculate, not 1 to 2, it's Q2 2 to 3. This equation I use to calculate the heat in, which is Q2 to 3. So let me try and erase over here, make some room. That's exactly right. When you have the cold air standard analysis, you must use that. So from 2 to 3 is equal to C sub V T3 minus T2. Just taking that equation. True? And we have our temperatures, and there's our specific heat. And so we calculate Q2 to 3, and that's equal to 260 kilojoules per kilogram. That's the answer to part C. What is the net work for the cycle? The net work is going to be the sum of all the W's, 1 to 2, 2 to 3, 3 to 4, 4 to 1. But we know 2 of those W's are 0. We talked about that. 2 to 3 and 4 to 1 are 0 because there's no expansion, no change in volume. So there's only 2 W's. 1 is going to be a positive W. 3 to 4 is work out. 1 you're going to calculate to be negative. So when you add them together, you'll still have a positive entity, work net positive out. Okay. So what is this work 1 to 2? Well, here's the equation. So that's going to be C sub V T2 minus T1. True? I made a little error. What's my error? A sign error. In my general equation, I have delta U is equal to Q minus W. I forgot the negative right there. So when you do that, you calculate that this work 1 to 2 is equal to negative 314 or 5 kilojoules per kilogram. The work 3 to 4 is a positive 469 kilojoules per kilogram. So the work net, trying to economize on space, is about 154 kilojoules per kilogram. Now the last part, what is the thermal efficiency? The thermal efficiency is that work net divided by Q2 to 3, just the in part. And you've calculated the thermal efficiency to be 59.4%, a whopping 59. Now you're not going to get that thermal efficiency, but it's what's predicted from these assumptions.